Hello and welcome to the last part of Module 5. Hopefully this last part will be quite exciting. The plan is to describe to you a puzzle, make you think through it, and show you its solution. I believe that at the very least, this should make you understand better what you've learned so far, and in the best case, this puzzle will leave you completely fascinated by quantum mechanics. So here is the puzzle. Imagine a box which could be containing a firework. Now, if the firework is present, the firework is designed to set off, to explode, as soon as it is hit by a single photon, a particle of light. So what this means is that if you shine a photon through a hole in the box to simply see if the firework is present, this will make the firework explode. It will set off. Now the box has two holes on two opposite faces so that you can send in light from one side. Now, if you do so, you will either see the light come out on the opposite side, in which case you conclude that the box is empty, or you will not see light coming out, in which case you conclude that the firework was present to block the light. Of course, if this happens, the photon-sensitive firework will explode. So the question is there a way to find out if the firework is present or not without letting it explode? So no tricks, no weighing, touching, or interacting with the box in any way but with light and the two holes. So I encourage you to take a moment to think about this, perhaps stop the video. So it seems pretty clear that this puzzle is set up so that it is impossible to succeed. Right? Basically, the only way to know if the firework is present or not is to shine a photon at it, but once you do, it explodes. And you can take a moment to convince yourself that this is the case. And now that you've taken a moment to convince yourself, let me tell you that quantum physics says that there is, in fact, a way to succeed. And the solution is given by this circuit. So let me explain to you the components of this circuit. So in this circuit, there are two mirrors in blue. A mirror simply reflects any photon that hits it. There are two beam splitters. A beam splitter either lets a photon go through or it reflects it. So these two options happen with equal probabilities. And then there are two detectors which are labeled A and B. These are orange in the picture. And these simply record any photon that hits them. Then in purple, there is a source which emits photons. And finally, we have placed a box for which we don't know whether there is a firework inside or not. And we've placed it between a beam splitter and a mirror, sort of on a lower path of the photon. So let's try to understand how this circuit behaves. And let's start with the case of no firework. So the case in which the box is empty, which is essentially equivalent to there being no box at all, since the photon simply goes through unaffected. So what do we expect to see classically? Okay, so a photon is fired by the source. The question that I ask you is, what fractions of photons do you expect to see landing at detector A, and what fraction at detector B? So let's go through a simulation of what we think might happen together. So the source is emitting one photon at a time. When the photon hits the first beam splitter, half of the time it is reflected, so it takes the upper path, and half of the time it is going through, and so it takes the lower path. Either way, after hitting a mirror, it reaches the second beam splitter, and there half of the time it is reflected and half of the time it goes through. So either way, overall, we expect the photon to land 50% of the time at detector A and 50% of the time at detector B. So far what I've said shouldn't be surprising at all. It turns out, however, that this prediction is false. This is not what you observe when you run this experiment. And much like with the double slit experiment that we saw in module 1, what we see here does not align with classical intuition. And this is because the photon is a quantum object. It is not a classical particle. And moreover, it turns out that the beam splitter itself is a quantum gate. And recall that we've just talked about quantum gates in the previous video. In fact, it turns out that the beam splitter is not simply reflecting half of the photon and deflecting half of the photons, but rather the beam splitter is transforming an incoming photon, say incoming from the left, into an equal superposition of being reflected and going through. So here we're talking at the level of quantum states, not classical particles. So a bit more visually, the beam splitter is acting as follows. It's taking a photon incoming from the left, and it's transforming this photon into an equal superposition of a photon exiting upwards and a photon exiting to the right, respectively reflected and going through. And at the same time, the beam splitter maps a photon that is incoming from the bottom to an equal superposition of a photon exiting upwards and a photon exiting to the right, except that the relative phase is different. It's a minus instead of a plus. And so the beam splitter is acting very much like a quantum gate. And in fact, a photon incoming from the left or a photon incoming from the bottom, these two correspond to two different quantum states. And now if you stare at these two transformations for long enough, you'll realize that they correspond to the Hadamard gate that we encountered in the previous module. Now recall what the Hadamard gate did. The Hadamard gate maps ket0 to 1 over square root of 2, 0 plus 1 over square root of 2, 1. And it maps ket1 to 1 over square root of 2, 0 minus 1 over square root of 2, 1. So this transformation has precisely the same structure, the same form as the one we saw in the previous slide. Where here, before the photon hits the beam splitter, we're associating the states ket0 and ket1, respectively, with photon incoming from the left and photon incoming from the bottom. And after the photon goes through the beam splitter, we associate ket0 to the photon exiting upwards and ket1 to the photon exiting to the right. Now, what you may ask is, how do we know that the beam splitter acts precisely in this way, like a Hadamard gate? And the answer is that this is simply one possible modeling choice, but it turns out that if you do make this modeling choice, then the predictions derived from it match with what you observe when you actually run the experiment physically. And so how does this circuit behave when we actually reproduce this experiment in a lab? So it turns out that if you actually run this experiment in a lab, what you'll observe is that the photon lands 100% of the times at detector A. So this in itself is quite a surprising conclusion. And so now all we need to do is to understand why this is the case. So what is actually happening? So think of starting with a photon in the state ket0, which we take to represent a photon incoming at the beam splitter from the left, which is what is happening in our circuit. Now, don't worry too much about ket0 and ket1 and what they represent. ket0 and ket1 are anyways just placeholders for some physical states. Okay. Now, after the first beam splitter, the new state of the photon will be 1 over square root of 2 ket0 plus 1 over square root of 2 ket1. Okay, where here ket0 represents the photon exiting the beam splitter upwards, so it's being reflected, and ket1 represents the photon exiting to the right, so going through. And again, the fact that the beam splitter behaves in this way is just a modeling choice that we made. And so we'll see if the predictions from this modeling choice are in accordance with what we see in the actual experiment. So now we have a state which is a superposition of upwards and going to the right. So now we have a state which is in an equal superposition of the photon taking the upper path and the lower path. And so now, either way, the photon will hit the second beam splitter. And so what is the state after hitting the second beam splitter? And so again, the second beam splitter will act as a Hadamard gate. And so we can calculate exactly what the state of the photon will be after passing through the second beam splitter. And so we'll dissect together this calculation right here. So we have H that is applied to 1 over square root of 2 ket 0 plus 1 over square root of 2 ket 1. Now, by linearity of the action of a quantum gate, this is equal to 1 over square root of 2 H0 plus 1 over square root of 2 H1. Now we're in a position to substitute the values of H applied to ket 0 and H applied to ket 1. And this is how we obtain the second line. Okay, we're just plugging in the values of the images of ket 0 and ket 1 under the Hadamard gate. So in the second line, we get 1 over square root of 2 times the image of ket 0, which is 0 plus 1 over square root of 2, plus 1 over square root of 2 times the image of ket 1, which is 0 minus 1 over square root of 2. And now to obtain the third line, all that we do is to just expand this expression by using the distributive property, which applies to vectors as well. And what we get is a half ket 0 plus a half ket 1 plus a half ket 0 minus a half ket 1. And now this minus is really crucial, because now if we group the ket 0 terms, we get a half plus a half, so they have the same sign. But if we group the ket 1 terms, we get a half minus a half. And so the ket 1 term vanishes. Another way to look at it is that the amplitudes for ket 0 are interfering constructively, and the amplitudes for ket 1 are interfering destructively. And so what we're left with at the end of the calculation is simply ket 0, which we take to represent the photon exiting the beam splitter upwards, and so landing at detector A. And so again, much like in the double slit experiment from module 1, interference is playing a crucial role. And because of interference, the photon always exits the second beam splitter upwards and lands at the detector A 100% of the times. So in fact, the effect of interference in this particular experiment is even more dramatic than in the double slit experiment, I would say. So now that we understand how the circuit behaves when the box is empty, let's understand what happens when there is a firework in the box. So the key observation here is that the firework acts as a measurement. It forces the photon to basically decide whether it's taking the upper path or the lower path. And why does this count as a measurement? Well, this is because we are extracting a bit of classical information. Namely, if we see the box explode, then we know that the photon has taken the lower path. And if we don't see the box explode, we know that the photon has taken the upper path. This is a bit of classical information, and hence the firework in the box does induce a measurement. And so let's analyze concretely what happens. So after the first beam splitter, the state of the photon is, again, 1 over square root of 2 ket 0 plus 1 over square root of 2 ket 1. And now at this point, we're performing a measurement. And the measurement is asking the question, is the state of the photon ket 0, which is essentially taking the upper path, or is it ket 1, which corresponds to the lower path? And now by Born's rule, which we have studied in a previous video in module 5, so if you have forgotten it, I encourage you to go back and watch this video about measurements. Now by Born's rule, with probability a half, the measurement outcome that we see will be outcome 1, which corresponds to the photon taking the lower path. And in this case, the firework sets off, it explodes. Now, on the other hand, again, with probability a half, the outcome will be 0, corresponding to the photon taking the upper path. And so the firework does not set off, the box doesn't explode. And so the question now becomes, what happens to this photon once it reaches the second beam splitter? So to answer this question, first of all, we need to remember what happens to the photon condition on obtaining outcome 0. So by Born's rule, if we obtain outcome 0, so if the photon has taken the upper path, then it means that the photon has collapsed to the state ket 0. There's no longer any amplitude on the lower path. And so now when we apply the Hadamard gate corresponding to the second beam splitter, we end up with the image of ket 0 under the Hadamard gate. And the image of ket 0 is simply an equal superposition of ket 0 and ket 1. So an equal superposition of exiting upwards and exiting to the right. And so there is no longer any interference. And so what we will observe is that the photon will land at detector A 50% of the time, and at detector B the other 50% of the time. And so I encourage you perhaps to take a moment to pause the video and take your time to think through all of the cases that we've covered. So I'll be doing a recap in the next slide. So basically, in summary, in the case that the box is empty, what we saw is that the photon always hits detector A 100% of the times. On the other hand, when the box does contain a firework, well, 50% of the times, no photon hits any detector at all because the firework has exploded. The photon took the lower path and the firework exploded. And then in the case that the box does not explode, half of the times the photon will hit detector A and half of the times it will hit detector B. So overall, we have another 25% of the times where the photon hits detector A and 25% of the times where it hits detector B. Now, the really big deal is the last case. So when the photon hits detector B. Now, the reason is that in this case, we are certain that the box contains a firework. But we learned this without setting it off, without making the firework explode.